very much, first of all, for the invitation, and I'm happy to speak to you about the work that was done in collaboration with Emily, who was actually mainly doing most of the simulations, Zheng and Yin Chen. And I'm touching back upon a scheme that apparently is kind of stretching through the whole week, starting from the first talk by Wei until the last talk by Zheng. So I will also be interested in the critical theory that was proposed at some point for the transition, direct transition of the Néel order to the VBS. Since we have seen this quite a few times, I will be quite brief. But the version that I want to focus on is the one where you intertwine the Néel order and the VBS order in this nonlinear sigma model, which would naturally explain the numerically observed, at least approximate SO5 symmetry. Now, borrowing back on the slides that, or ideas and results that were presented by Wei, on one hand, when we write down the nonlinear sigma model, we know that in the weak coupling limit, we can have a spontaneous symmetry broken phase related to first order transitions between Néel and VBS. And at least for large n, for example, if you take large SUN spins, there's one can show that a consistent conformal phase exists separated by a phase transition from the spontaneous symmetry broken phase. So this is pretty much the scenario that Zheng was also alluding to in the previous talk. But on the other hand, the numerical data for the fuzzy sphere showed that if you simulate the SO5 symmetric theory, that there is a singlet scalar which can flow, for example, from being slightly irrelevant to slightly relevant. And this was connected to the idea of fixed point annihilation, where the two CFT points meet and form then a complex CFT, so it would show up as walking behavior. And the rest of the talk will be pretty much focusing on the critical NC. So can we find a generalization that Zheng was already introducing, and show that in some cases we might only see the symmetry breaking phase. In other cases, we hope to find the stable conformal phase instead. So let me remind you briefly of the generalization that was already introduced in the previous talk. We are coupling, or we are looking at SPN symmetric models. In contrast to before, I will be staying at half filling. This has to do then later on with the sign problem in the Monte Carlo that I would suffer if I go to any other filling fraction, at least as far as I understand at the moment. And for the SPN group, we will have 2n flavors of fermions in the Hamiltonian, so that we first start with an SUN symmetric term if we only consider density-density like interactions. But then we can also introduce essentially a pairing operator, delta, which breaks the SUN 2n symmetry down to SPN symmetry and allow for these pair correlation terms. One thing that I would like to point out already is that on one hand for SP2 this would be isomorphic to the SO5 symmetry that was discussed in Wei's talk. And the other thing that I find quite useful is to essentially split these 2n fermions that we have into two groups of n flavors. And then I have an effective two-level system between the two groups, and this is encoded by this 2x2 Pauli matrix here with the same structure as there, and then we have the identity matrix on the diagonal. This will be later very useful for the efficiency of the Monte Carlo. So I wanted to discuss a little bit about how we actually implement this in the Monte Carlo, because I think there was no other presentation on Monte Carlo simulations of the fuzzy sphere. So, but we are using the same general software package that Fakir also used for his lattice simulations. So we start by taking the continuous fields, like usually in the fuzzy sphere simulations, and project them down to the lowest Landau level. So we effectively end up with fermions, where on one hand I have this orbital degree of freedom from the Landau level. On the other hand, I have this sigma between the two groups of n fermions, and then I have the alpha index running from 1 through n. When I arrange the operators such that I characterize a 2-fermion operator by the angular momentum and the C component of it as the center of mass momenta, I get a Hamiltonian which takes this form. So I have a sum over all the center of mass angular momentum, where the coupling constant can be L-dependent, and then I have typically the n dagger n interactions for the SU2 symmetric part, and I get these delta dagger delta terms for the SPN symmetric interactions. And then, like we typically do when we do Monte Carlo simulations, we're essentially interested in the partition sum C as the trace of e to the minus beta h. So technically speaking, I'm doing simulations at finite temperature, but we will be scaling the temperature with the system size to approach the 0 temperature limit. And I go through the usual techniques by trotterizing the e to the minus beta h, and then introduce Hubbard-Svatovich fields, making use of the small delta tau, which in this case, I've written them out here, take the following form. So we have one field that couples to the density with this peculiar phase structure. And on the other hand, we have fields that couple to the Hermitian and the anti-Hermitian part of the pair creation operators. And it's relatively easy to work it out that if you look at the squares of these terms, you can massage them to bring them exactly to this form up here. So these are, we will be, the advantage now is we have effectively, for a given auxiliary field snapshot, we have non-interacting fermions and can use all the nice properties of Gaussian theories, but instead we then have to average over these auxiliary fields. So one of the questions one should ask now is, if I want to average, stochastically sample the Hubbard-Svatovich fields, will I have suffer from the sign problem or not? And as Fakir had already hinted at, if I can find a anti-unitary symmetry, which essentially ensures that the matrices that will appear when I integrate out the fermions have to have eigenvalues as complex conjugate pairs, then I know that the determinant at the end will be positive. Since we have repulsive density interactions in the U term, we will have to work with particle hole symmetry, because otherwise, just by the sign structure, I don't find an anti-commuting symmetry here with the density operator. And that limits us to half filling. So all the whole family that Cheng introduced, we can only stick to the 2,1, 4,2, and so on, subclass of them. And we can show that for the sign of the V interaction that we are interested in, that Cheng was already introducing, we will have to find essentially a symmetry that can ensure the squaring of the particle hole symmetry to -1. And for this, we have to split the n flavors, where the alpha index run over, again into 2 subgroups, so that we can exchange them with the alternating minus sign, similar to a spin transformation. So we will be able to do SPN symmetry simulations as long as n will be even.
Can I ask a question?
Yes, please.
So of course it's good to have a proof that in this case the determinant is real. But in other cases when you don't have a proof and you suspect that it's actually doesn't exist, can you just make a test? You know, pick some values of compute the determinant for one point and see if it's real or not.
Yes, you can. The problem is that often enough one does find negative configurations when you go deep into the sign will scale with the inverse temperature and the effective system size. So if I am at high temperature on small systems where I can do fast simulations, it can happen that they only show up very, very rarely and I just don't see it. I could say for practical terms, okay, well, if they're so rare that I essentially never see them, then I don't really care about them. Yeah. So yes, one can in principle always try, but it's also a bit of work in setting up the Monte Carlo, so you have to find your balance. Okay. I'm actually not sure, Emily, maybe you can remind me, there are some models where we don't understand why there isn't a sign problem, but we haven't seen negative configurations. And I think actually the Ising model itself with the two flavors doesn't seem to exhibit a sign problem, but we don't know why. Or we didn't go low enough in temperature or large enough in system size to eventually find negative configurations. Yeah. That's right. There is another unfortunate price that Fakir was already alluding to. Since we essentially formulate the method in momentum space, local interactions are non-local in momentum space. Like local real space interactions are not necessarily local in momentum space. And this implies that the algorithm, the numerical effort, doesn't scale cubic like it usually does. But it definitely has to scale to the fourth power in the naive implementation. And if you now include that the trotter step size might have to be reduced with the system size, it can be even worse. There is another nice benefit.
Did you notice this in your simulation?
No, doesn't seem to be the case. At least the delta tau values that we were using from the beginning were small enough so that there was no trouble.
Question?
Yes.
Why do you need to go to small delta tau, or particularly small?
We initially have this e to the minus beta h, where h is a sum of non-commuting terms. But we want to decouple we want to bring the Hamiltonian to a form where we can use perfect squares for the Hubbard-Satonovich. And when I look at an isolated e to the minus a squared, but to rearrange the terms in the Hamiltonian to isolate these terms, I would have to deal with the commutation relations between the different perfect squares in the Hamiltonian, which requires the Trotter discretization.
I understand, but if you're not actually interested in like exact energetics, but you're just thinking of this as a StatMat model and a universality class, do you really need to take the delta tau to zero limit?
I mean, if you leave delta tau finite, you essentially introduce kind of a high energy cutoff. But I'm not sure if there's maybe some subtle interplay. Fakir seems to have a comment.
You could in principle, but you have to be very careful because the trotter could, for example, break the hermeticity of the propagator.
Yeah.
And if that happens, you plug in something you don't control anymore. You know. Well, I mean,
but
so
the size of delta tau should not matter in that.
Well, it depends, right? I mean, if you have a very big delta tau, then the correction you have, the correction is proportional to a commutator of two parts of the Hamiltonian. That can be pretty big, and that will add a big non-hermeticity in the imaginary time propagation, and then things can go dramatically wrong.
But I've done this before with the TV model where in my formulation you didn't have the broken hermeticity.
And then you can do that maybe. So I think the answer is, if you respect all the symmetries, you're good, right? But you have to be sure to respect that you can break symmetries when you do the trotter, and if you don't control this, if you break those symmetries, then you have to be very small delta tau. If you don't break the symmetries, then I think you're right. You can go to big delta tau and get the right stat mech.
So do you break symmetries with the trotterization? That's the question.
We are not breaking the SPN symmetry. I think by trotter itself, probably not. With the auxiliary fields now, I'm wondering if we have to restore the rotation symmetry on average, because I have different field values for different angular momentum, especially.
That's okay. I mean,
yeah.
That happens always.
Yeah.
But, in the stochastic average, do you break symmetries? That's the question.
No, I don't think so.
Yes, but there's one nice property now is that in this language of the auxiliary fields for a given snapshot, the Hamiltonian is essentially block diagonal in this alpha index, and all of the alpha blocks are identical. So what this effectively means is that when we look at our Monte Carlo averages and the weight, the hard part is to calculate the weight, and this will just be taken, or I take the determinant of the two flavors and raise them to the power of 2n. So it virtually has hardly any numerical expense to go to large n. And this is like the big advantage of these simulations. The disadvantage is that we don't do exact diagonalization, so we don't have immediate access to the spectrum and the energy eigenvalues. Instead, we have to calculate correlation functions either in space or in time to then extract the energy levels from the time decay rate. And for this, we need to match the operators and check which kind of quantities do we have access to. The most important quantities or operators that we found and could match is, on one hand, the symmetric rank 2 tensor in the SPN space, which should have or which shares the same symmetries with the symmetry current and should overlap with it. And then similarly, we are looking at the antisymmetric rank 2 tensor, which is odd under parity and overlaps with the phi field. So the question that we really want to address, and now I'm starting with SP10, can we tune the system by varying V from a symmetry broken phase to a symmetric phase? And here I'm plotting the antisymmetric tensor correlation function, where I converted the data obtained in the angular momentum space, here explicitly written in terms of the angle theta, but we can also further convert the angle theta into the actual distance between the 2 points across the sphere. And I'm plotting this on a log-log scale. On the left, for weak coupling, where the V interaction term is set to 0.2, on the right-hand side it's 8. And there is a distinct difference that there is a kink in this data which systematically is absent here. And this was the first hint. Maybe the correlation function starts to flatten out, indicating spontaneous symmetry breaking at weak coupling, and this development of kind of long-range correlation functions is absent in the other interaction value.
What does the G-flow diagram look like if you just have one thing? Is red supposed to be a CFT?
Yes. So this is an analogy to this. That
it's the first one.
It's the first. It would be the first one. So the red dot that I had on the axis would be the CFT separating the symmetry broken phase from the conformal stable CFT phase. Yeah. And the question is, do we find this point for the value that we have here? All right. So this is, of course, not at all precise yet, but then thanks to Francesco at the beginning of this week, he was pointing out a nice RG family, actually, of RG invariant quantities. We only tried the first one, where you essentially take the correlation function at two different angles and take the ratio thereof. So this is on one hand RG invariant. It's also insensitive to any sort of normalizations in our operators. So it's a very practical and easy to access quantity. So the data that I show here in the main plot is data where I take the correlation function where theta is pi half and take the ratio with theta at pi, trying to aim at the long distance behavior of this correlation function. And as usual for RG invariant quantities, and here I'm really only talking about scale invariance in the first part of the analysis, is that I detect symmetry breaking when with system size the data is systematically increasing. And this is the trend that I see on the left hand side, while on the right hand side at stronger coupling I start at somewhat large values at small system sizes and reach lower data for large systems. And in between, there seems to be a relatively nice crossing point here, which would indicate the phase transition between a symmetry broken phase and a symmetric phase. So we are tempted to essentially draw a dashed line here separating the two, and the red dot of the phase transition, the CFT describing the phase transition, should be located somewhere around here. All right. So next, we can proceed by essentially analyzing the correlation function CA.
Can I ask a question?
Yes.
So, I presume that you can do this for some volumes which are much larger than accessible without quantum Monte Carlo, but how much larger? What can it do?
So at the moment, it's...
Well, first of all, none of these are accessible at any level orbital.
I'm sorry, couldn't hear you.
So for SP10, none of these would be accessible for any number of
because the cell is so large. Yeah, thank you.
Yes.
One orbital has.
Thank you, thank you.
Yes. So I think this is 20 orbitals times 20 flavors. So this is 400 orbitals. Yeah.
Thank you.
And I think we have a chance to push the Monte Carlo to even larger systems.
So question, so how about V equals 2? All of the sides merge together, what happens there?
Yes, a very good observation. It's an RG invariant quantity. So ultimately it should also pick up the scale invariance of the conformal phase. So I would expect if I really go that far to say I will have a conformal phase at large V, it should become size independent again at large V. So in the thermodynamic limit, I would expect in this scenario a flat line which jumps to another value at the transition, and then something that probably goes to 1 in a properly long-range ordered phase. So it's essentially like a theta function with a point in between at the jump, where 1 is the value for the stable CFT, and the point is related to the CFT of the phase transition.
Okay, but why couldn't this be the other CFT?
It is.
So I mean, you said okay, there when there is a crossing, it's one CFT, and there it's the other CFT, right?
So what you're like, one interpretation of this data is that if you are on this point, but to the left, you see the flow from away from the repulsive fixed point towards the symmetry broken phase.
Okay.
If I am very close to this point here, crossing point here, but to the right, I should ultimately flow to the stable phase.
Okay, good.
But it shouldn't be there immediately on a finite size system. This is actually the perfect switch to the next slide, because here we are now taking the antisymmetric correlation function, take the longest distance at theta equals pi, and now scale this correlation function as a function of the system size, and extract the scaling dimension of the operator phi in the usual scaling analysis sense. And this is the data that we report here on the as these blue curves, where for a conformal phase you would precisely expect a constant value for this critical point, or for this operator scaling dimension, independent of the coupling V that we have. Now the question is, how does this scale with system size? Or can we make use of the conformal symmetry? So the first attempt is I will show more systematic data, but using this ansatz, I can calculate the logarithmic derivative in the r direction, for example, at the theta equals pi point, to extract the delta value. And once I have delta, I have essentially fixed the full correlation function up to the prefactor. So here I'm now plotting the CFT expectation as the dashed line and how finite system sizes approach this, where the antisymmetric correlation function is plotted as the whole across the whole spectrum in theta. And to have a little bit better resolution of potential deviations around theta equals pi, I'm also showing, sorry, there is a label missing. This is not CA, but it's the derivative of CA. So how well does the function itself and how well does its first derivative agree with the expectations from conformal field theory? So I already mentioned that we can take logarithmic derivatives in the radial direction, but we could also imagine taking logarithmic derivatives with theta, using the second expression to extract also the critical exponent, or the scaling dimension delta here. And the nice thing is we can do this for all different system sizes. And this is the collection of these plots, where again I'm scaling the V interaction term strength. The phase transition was happening at, I think, 0.03, somewhere down here. And for this large V range to be in the conformal stable phase, we would expect, again, this flat line here, independent of system size. We notice the trend so that it, with increasing system sizes, we really squeeze into the corner as a hallmark of the RG flow away from the critical point, the other critical point that should somewhere sit over here. What's kind of interesting is we can do this analysis for different theta angles. So for example, at this point on the sphere, then for a little bit larger values, even larger theta values. And one trouble that arises, which is also poisoning the derivative in the r direction, is that the first order derivative would suffer from the sine theta in the tangent going to 0. So we will pick up a bad signal to noise ratio at large twist angles. So we want to go to large distances, but we can't go to the longest distance we have. And you see this by the noise that is starting to creep in when we approach theta equals pi. And at the theta equals pi, the first derivative actually vanishes, and we would have to go to the second derivative, which is even worse signal to noise ratio. But this is effectively the same as taking the derivative in the r direction, perpendicular to the sphere that we actually have.
Yes. So this delta phi, I don't understand the flux on the right. Is delta phi you're measuring over the entire V, but you're saying you have two fixed points, one conformal and dependent V, and one at the crossing. So what does delta phi means?
Well, I mean, the claim is that we have the fixed point transition as a transition from a symmetry broken phase into a conformal phase. But the whole conformal symmetry should apply to the whole range once V is above VC. Right. I may have to go to larger system sizes to actually see the scaling behavior.
But then you have two values of delta phi.
Yes.
But here you see an entire curve. That's what I was not understanding.
Yes.
This delta phi has an entire curve.
Okay. So the interpretation is that that systematically, if I go to larger and larger systems, once I'm above the critical value, this curve flattens out, becomes constant and size independent, and that's the delta phi for the stable conformal phase. And it should jump to another value, which is the delta phi of the phase transition. And then it's no longer well defined once I'm in the symmetry broken phase.
So the curve you're seeing there in between is not a crossover phenomenon. This delta phi you're seeing that goes from 0.3.
So
No, so I'm interpreting this, the curve that you have here as essentially the as signs of the RG flow, where if I start close to the fixed point of the phase transition, it takes some time to reach.
Exactly what I was saying, crossover.
Yeah.
But on this plot, can we see the value of delta phi of the unstable CFT or not?
no. Well, at least I can't.
Okay. But you would have seen it if there were some nice crossing points or.
Yes. 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 So ideally, you would see the plateau here and then a crossing point right at the transition, but I can't make it out.
It doesn't have to be crossing for the phase transition. It could be just the approaches to the higher value from one direction.
Yeah.
Because here you already rescale, but maybe it wouldn't be crossing at all, because in this plot you're already rescaling by some power of n to arrange for a plateau at large. To arrange for a plateau.
No, here we're not rescaling. We are taking the theta derivatives of the correlation function. And the shape of these curves mimics the behavior that we extract when we scale the expected phi correlation function with system size. Right. So we took this as a very positive sign of finding actually the stable conformal phase. We can also try to attempt the energy eigenvalues, but we have to take an indirect route by calculating time-displaced correlation functions. And we actually were quite surprised by the length scale and the data that we find. So what we are looking at here is for zero angular momentum, the time-displaced, imaginary time-displaced correlation function, which starts as an order 1 number and then decays down to 10 to the minus 20. And this is very, very unusual. Typically, you pick up noise on the level of 10 to the minus 3 or 4, depending on how good of a statistic you have. But it's very rare to resolve more than 2 or 3 decades. And I don't understand why the quality of the plots is so high. And we extract the slopes of these correlation functions. Here's an example for the antisymmetric zero angular momentum, and then antisymmetric but at angular momentum 1. And we can do the same for the symmetric combination at angular momentum 1, which should be the symmetry current. And the results are plotted here, where if you drift from the right to the left, you are going from smaller to larger system sizes, similar to the plots that we saw before, just I have, not the best color coding. And this is in the antisymmetric sector and in the symmetric sector. And we fixed the level spacing between those two energy eigenvalues to be 1 to normalize the speed of light. And I leave it up to you to interpret the precision of the energy values that we can get in this way. But okay. So when we put everything together, for example, here we are looking at the coupling constant of...
Can I actually ask a question at the first plot? So here you have periodicity in the time direction.
Yes.
And 70 means 70 steps, and after 70 steps you are periodic?
Yes. Yeah. Yes. So the imaginary time beta is 70 in this example.
So is it okay that, say, you don't see deviations from power laws at, say, quarter period?
Okay, here I'm actually, sorry, I didn't say this explicitly. I'm actually showing this on a logarithmic scale.
Yeah.
So it's an exponentially decaying function.
Oh, okay.
Typically, you would expect indeed multiple scales because here we should pick up all, by symmetry, we should be able to pick up any excitation that has this antisymmetric tensor representation and zero angular momentum. Mm-hmm. And there definitely should be higher energy excitations, just if I think of the box descendant. Yeah. I don't understand why it seems to be a single exponential decay rate and why the overlap of this operator with the box phi is so small that we essentially only pick up phi itself as the lowest state.
Yeah, but the overlap goes to 0 when the cutoff goes to infinity. So, right?
Yeah, but
the primary is always going to be suppressed by the cutoff.
Okay, I'm not sure if I understand the statement, but maybe I'm happy to discuss afterwards. Yeah. All right. And then, okay, these are the nice plots if we go to larger angular momenta, or if we go to the singlet channel, the data is very soon much noisier, and it's barely possible to extract other energy scales. But taking this imaginary time data for what it is, we can compare the scaling dimension of phi that we extract from extrapolating the correlation function with the system size indicated by the black line. We can extrapolate or analyze the scaling dimension that we get from taking the logarithmic derivatives in the theta direction and the energy eigenvalues that we get from the correlation functions in imaginary time. And at least I would argue that they are consistent.
Could you do the Y scale for a moment? That's just sort of covered.
Sorry? Sorry. The Y scale is from 0.6 to 2. And the black line sits at 0.8. Sorry. More questions? Okay. So if we put everything together, at least I find the numerical evidence quite convincing that there is indeed a transition in the SP10 symmetric model from a symmetry broken phase at weak coupling to a stable conformal phase at strong coupling. So 10 should be above the NC in this scenario. With this in mind, we can move on and look at the SP4, the closest we can get without actually simulating SO5, SP2 symmetry. And now let me walk you through this maybe a little bit faster. We have, again, this correlation ratio at pi and pi half. And we see, again, the scaling with system size where it goes up at weak coupling and somewhat goes down at stronger coupling. Here I'm showing a zoom-in of the same figure. And while there are more finite size effects and the data is maybe less clear than in the SP10 case, I think we can still suspect that there is a transition between the symmetry broken phase and very likely again the conformal phase at a coupling constant closer to 2 this time. But one thing that we should probably do in the future to analyze maybe also the scaling with system size of the crossing points, is there a drift and how confident can we be that this actually holds up? Similar to before, we take these logarithmic derivatives to extract the scaling dimension of phi in that way from the equal time correlation function. And it's definitely not as flat as it used to be. and the drift to generate this stable plateau is not as strong as it was for the SP10, but I think the trends are still going in the right directions. We're just seeing much slower flow of the quantities that we are looking at. So we can do the same energy analysis, looking at the energy spectrum and also at the consistency between the three different ways of extracting the scaling dimensions for phi for a value of v.3, which should be in the outside the symmetry broken phase, and it would again suggest consistency. So hence, one could speculate that this is conformal, even though I admit that the quality of the data here is now not as precise as it used to be.
And the black line is what you got from exact diagonalization?
No, sorry. The black line is the data I get when I plot the correlation function at theta equals pi, the longest distance that I can have, and scale this value as a function of different system sizes. So the usual RG scaling analysis that you can do on any lattice where you take the longest distance and see how this value scales with system size as a proxy for the order parameter squared.
And what did you get from ED?
We don't have ED data here.
How about it's SP4 as well?
And we don't have ED for SP4 as this many orbitals. We did the spin.
Yeah, okay, but I mean, from the previous talk,
Yeah.
must have been an answer for this thing, right?
Much
fewer
smaller
orbitals,
systems, but nevertheless.
Cheng, do you remember what values you got? I'm not sure if we have the same V value, but yes, you're right. We should check against ED, but I don't think we have quite the same value, because also the way how Cheng was tuning to the ideal, the most conformal point is something that is much more expensive here and not.
Yeah. But according to your talk, right, the scalar, the number for the singlet, exemplifies SP4 singlet, was 3.02 something. I remember that very well from your slide. Right? So you should be somehow on your lattices. You should be somehow in a walking or some. You should not be able to draw any. I would expect not to be able to draw any conclusions based on your.
Yes. So we have So unfortunately, precisely the interesting scalar that determines the walking and the stability of the CFT is something that we don't know how to address. We don't have. I understand that we have his data, and it's the same model. And what is true, what I'm trying to say is we can't directly compare those numbers. But what is true is that if you look at this data, this is essentially how it would show up in our simulations, that you can compare the crossing between the, let's say, 6th and 11th orbital, and then you compare the crossing between 11 and 15 and so on, and you ask, how does this scale with system size? Is there a constant trend so that the crossing between these pairs of system sizes is constantly shifting to larger and larger V? And at this moment, we don't have this analysis because this is pretty fresh data, but this is definitely something that we want and should look into to see if we find this walking towards the symmetry broken phase.
The question, I think, is that even if it's not walking, even if it's a CFT, it's going to be a CFT with an operator which is just barely irrelevant, so you should see very strong, almost logarithmic corrections to scaling.
Yeah.
And for the moment, we say the corrections to scaling look large, but you don't really know if they're logarithmic or maybe it's better than logarithmic.
At this point, we don't know yet. We'll probably have to refine the analysis in this direction.
But it's probably fair to see that this RG flow is much lower than.
Yes. So it's definitely fair to say that the RG flow here is much slower than it was before. If it's slow enough, or if it's, yeah, I don't know. At this point, I honestly just don't know. And this is the data that we have. But we can compare with the results for SP2. So if I look at this correlation ratio for the SP2 case, we have the 5, 7, 11, and 15 orbitals from blue to red. And at least here, there's no discussion that the largest system is constantly above everything else. And from the SP2 plots, I would be relatively confident to claim that this whole range from 0 all the way up to 8 will very likely end up in the symmetry broken phase. But if I compare this to the SP4 by eye to me looks more closely related to SP10 than to SP4, admitting then there is a massively slower RG flow for SP4. So I guess I'll leave it up to you if you decide or trust that the critical value where the fixed point annihilation is or emergent is happening is above or below 4. This will depend precisely on this discussion. Does it drift?
But the question is the range of V sufficient or not? Maybe you should go to even larger V.
Yes, SP2 is seen as a flag.
Yeah.
Because from SP2 to SP4, V, critical V increased by factor 8.
Yeah.
No, 4, sorry.
Yeah. I think we have at some point also tried larger data and with larger V values, and we didn't see any systematically changes. But yes, this could also be something.
But for the critical value of different n, I guess it's probably just a normalization issue. Like probably normalization is that you may want to multiply n to the 2v.
I think we already multiplied n to v.
But maybe we should not.
Yeah.
Probably should multiply again. That's probably match.
Yeah.
I mean, yes, obviously, these are the open questions. Can we, could things change if we go to larger V? Maybe. Is there a hiding drift that actually also here these data will flow to look more like this if I go to much larger systems? But at the end of the day, this is the data that we can access at the moment. And while I admit the uncertainties of 4, I personally believe the critical value is probably below 4, but it's surely in the vicinity of 4.
But for the large V, I think Jen looked at it using DD, right? There's no significant difference.
Yeah.
The values should be.
Yeah. I think we have no indication to expect a change with going to larger
conformal
V.
symmetry, I think, but the quality of conformal symmetry becomes worse. That's the observation.
Yeah.
Question, sir.
Mm-hmm.
So in this calculation, did you calculate the ratio directly in Monte Carlo calculation, or you calculate the two quantities separately and calculate the ratio?
We calculate the two quantities separately and then take the ratio.
Is there any possible way in Monte Carlo calculation to calculate this ratio directly?
But maybe it won't be correct. Because the point is that the 2-point function scale with some power law if it goes to a critical point, and then the ratio of this power law then becomes RG invariant. But now that you compute the ratio in the Monte Carlo and the average, I don't know what observable would be. I mean, it's
going to be weird.
It's not really.
It comes into an observable.
All right.
It's a ratio to observable.
So
this would bring me to my summary. I have hopefully convinced you that we can do sign-free Monte Carlo simulations where for symmetric n we at least know that SPN is sign-free. Maybe it even works for odd n values without us knowing why. We have, I think, provided relatively strong evidence for the SP10 case that there is a critical value where we see the transition from the symmetry breaking to the stable conformal phase. The data for the SP4 is what it is, and either you believe it or you don't. Yeah, we show that there is agreement between 3 independent ways, or at least 2 independent ways, to extract the critical scaling dimension of the phi operator. And as an outlook to maybe help solve understanding the SP4 a bit better, is to improve the algorithm, similar to what Fakir was saying, where he can do hundreds of fluxes to really push for large systems. And it's also maybe worth to think again if we can find other observables or correlation functions to get access to additional CFT operators, particularly the S operator, which was dancing around 3, determining the stability of the proposed conformal phase. And I guess with this, I would like to thank you for your attention.
Any questions?
Yeah. Did you do SP6 or SP8? And if so, does it fit into the overall picture?
Yes. So we did do SP6 and SP8. We didn't spend as much resources on them, but it does fit into the picture. And I think already SP6, we can say a little bit more confident that it's more similar to SP10 than it is to SP4. And I didn't show the plot because sometimes it was misunderstood. But we can also track the delta phi as a function of n, and it seems to approach the expected value of 2 at large n. So it seems to smoothly interpolate between 4 and 10.
And large n. Mm-hmm. Yeah.
What is the gauge theory description of the operator heat correlation function you're studying, and what is the large n prediction for its dimension?
It's bilinear Gaussian, and then at infinite n will be half scale up.
Okay, so your 1.8 is close.
Yeah.
So what is that?
It's the Fermion mass.
Fermion mass.
Yeah, the symmetry breaking. SPN anti-symmetric representation.
So sometimes in lattice QCD, people do crazy things like raising Fermion determinants to non-integer power.
Yes.
Can you do this here, and does it give you any chance of providing non-perturbative definition of SPN theories with non-integer n?
Yes, I think we can do this, and in a previous project we were playing around with this on a lattice version of that model. For this specific simulations we haven't done it yet. So one way of essentially implementing this is to take the 2 flavor, like SP2 determinant, and then raise it to a arbitrary power that interpolates between any even n. And for any even n, we know that we match the integer and.
What do you do with the phase when you interpolate?
Is it clear that the positive root?
It's not a positive.
Well,
that's actually,
no.
I don't know. If the determinant was positive, then it's probably not positive.
So what I can guarantee is that m to the 2 is positive. And well, it's not enough, depends. You know, I can always do this to n, that will still be positive. And I can interpret this as 2n. And I now know that if I vary n as a rational number, whenever I hit an integer, I have a theory that I understand. These are the even SPNs. And with n, I'm interpolating in a sign-free way between them. I'm not necessarily knowing what, so I don't know what this rational theory in between would be. But it would be an interpolation between the even integers.
Okay. But didn't you say there was a sign problem for odd powers?
For odd powers, we don't know if there is a sign problem. And I'm not sure if we tried. Emily, did we?
All that is not defined. The model cannot define to all.
Microscopic model.
Yeah, microscopic.
No, I'm talking about SP3.
Right, that's what I'm saying.
Yeah.
You cannot define model for that at present tense. But you want half it.
Well,
Yeah.
yeah.
So then that's like SP 1.5.
Yes. Yeah.
So I agree with the statement crazy, but what makes it less crazy, which is a question, when you go to n, would the determinant have degenerate eigenvalues? So, I mean, if all the eigenvalues are the same as you go up, then it's legitimate, right? So if you did it directly for n, would there be degeneracy of the eigenvalues so that in fact the eigenvalues would just be multiples of determinants n squared?
Yeah.
If that's true,
So,
then
yes.
it's not crazy.
Yes. No. So this 2n, if n is an integer, is the direct result of having n block diagonal identical blocks.
Identical blocks.
Yes.
So then it's not crazy.
Yes.
That's perfectly okay.
Yes. So this n is the SUN intern.
That's crazy than what they do in QCD.
Yeah.
Yeah.
Yes.
But
So
then it's perfectly legitimate.
so for integer n, this is essentially an internal SU2 symmetry, which is a subgroup of the SP symmetry.
It's free lunch.
Because there are not so many ways to do this non-perturbative, right? There are these loop models, they're complicated, and not people haven't really done it. Here.
I mean, what we know, we can reinterpret this n, and we can write down something that will give results. And these results will match the results for the SP2, SP4, SP6.
All right. Yeah, Max?
Have you tried to fit the corrections to scaling to get the delta S?
No, we have not tried. But happy to hear more how to extract it.
But I mean, this is just the standard finite size scaling, right? You can leading irrelevant operator, then you can maybe try to see how the scaling dimension goes down to below 3 as n decreases.
Yeah, no, so one thing that I should maybe say is in the beginning we were struggling quite a bit to identify even the symmetry broken phase because we didn't have good estimates. So you would have, the Binder ratio is extremely hard to calculate here and very noisy, so that's not the good way to do. And if I think of taking the order parameter and then trying to do scaling analysis, I need an additional critical exponent already. And you have two CFTs close by, so it could flow in interesting directions. I guess what I'm trying to say is if I do the generic analysis of the order parameter in terms of finite size scaling, the fits were very unstable. And
What is the large V phase?
we haven't tried. I don't know.
Okay, thanks, Johannes. I don't see any other questions.
I think there are two more questions.
Two more questions? I'm sorry.
I have to turn around.
Okay. Because you have a question.
You probably already maybe mentioned. Did you look at Binder parameters as well?
We did look at Binder parameters, but it was hard. They were just higher point correlation functions and became quickly very noisy.
So the 100 fluxes we were mentioning were basically on the torus, right? Lana level on the torus. You're doing on the sphere. Is it harder on the sphere? You have more fluctuations? Do you know?
I don't think so. So I mean, okay. When we want to go to large fluxes here, we will have to reformulate parts of the algorithm. And we will have to move essentially to HMC-inspired global updates. Then we can gain back a power in the scaling of the algorithm. It goes back from n to the fourth to n to the cubed. But you also have all of these like little parameters that tune the algorithm and not the physics, where you can spend quite a bit of time to make it run efficiently. What's the right HMC step size and all of these, I don't know how you call them, super parameters, hyperparameters of your algorithm.
For this kind of calculation, I believe sphere is much better than Senindo or torus because many competing phases is forbidden here in this geometry.
So you would generically say we should give up the torus and go on, well, of course you'll say that.
No, but just for this, if you
For
want
this
to
one,
for this transitional critical phenomenon,
Yeah.
sphere is good because on Senindo or torus you may have many competing phases, SDW, CDW, many others.
Okay.
So you may stuck to
Right.
some, you know, some other phases.
Okay.
Yeah, well, I don't think that may be important here, but the really advantage of sphere is that you can still use conformal symmetry
Sure.
even if you don't look
Yeah,
at spectrum.
that I don't understand, but
Yeah. So Johannes showed this just by checking how the correlation changes with the theta angle. Just from that, you can get scaling dimension.
Yeah.
That's the most reliable way for us to get scaling dimensions.
And this was all done on a fairly small cluster, so we haven't really scaled up to massive resources.
All right.
Okay, this time it's no more questions.